model of ethene, C2H4, was constructed. Next, one of the carbon atoms was held with the left hand while the other carbon atom was gently twisted and rotated using the right hand.
First, a model of ethane C2H6 was constructed. Next, one carbon atom was held with the left hand while the other carbon atom was twisted and rotated.
First, a model of ethane C2H2 was constructed. Next, one carbon atom was held with the left hand while the other carbon atom was twisted and rotated.
Then, the distance between carbon centers in ethene, ethane, and ethine was measured and recorded, and the bond lengths were arranged in increasing order for single, double, and triple carbon-carbon bonds.
Then, a second model of ethene was built and both models were attempted to be superimposed.
After that, two molecular models of 1,1-dichloroethene C2H2Cl were constructed from model chloroethene. Both models with an attempt was made to superimpose them.
After that, two models of 1,2-dichloroethene were constructed from dichloromethane models by switching chlorine and hydrogen atoms. In the first model, similar atoms were placed closely together. Then, in the second model, similar atoms were placed farther apart and both models were thrown onto the bench. Next, the models were picked up and an attempt was made to superimpose them.
Then, two molecular models of bromochlorofluoromethane CHFClBr were constructed to be superimposed. Next, one model was placed on the bench. Without exchanging any atoms, the second model was rotated beside the first to produce a mirror image.
Next, two atoms of choice were exchanged in one of the models. Afterwards, both models were again thrown onto the bench, picked up and superimposed once more. Then, one model was placed onto the bench and without changing any atoms, the second model was rotated beside it to form a mirror image.
Afterwards, two molecular models of chlorofluoromethane were derived from bromochlorofluoromethane models. Then, both models were thrown onto the bench again, picked up and superimposed.
Then, the model of ethane was taken back and one of the short bonds in the model was rotated. The carbon atom farthest away, C2, was held with the left hand, while the nearer carbon atom C1 was held with the right hand, and the carbon atom C1 was rotated clockwise. Afterwards, the rotation of the front carbon atom was continued to 120 degrees and the corresponding new band projection was drawn and labeled.
Next, a model of hexanes was constructed. Then, the approximate bond angles between adjacent carbon-carbon bonds were measured and recorded.
Next, a model of cyclohexane was constructed from the hexane model. After that, two opposite carbon atoms were held from the top using both hands. Finally, with the left hand fixed, the other carbon atom was twisted downward towards the middle. This experiment was conducted to study isomerism and conformational analysis of organic molecules using molecular models. By constructing and manipulating these models, the three-dimensional arrangement of atoms and the effect of bond rotation were clearly observed, allowing a better understanding of molecular structure and behavior. In the first part, the bonding in ethane, ethene, and ethine was examined. Ethene was found to be planar and rotation around its carbon-carbon double bond was not possible due to the presence of a pi bond. Ethane, however, allowed free rotation because it contains only a single sigma bond. Ethine was observed to be linear and also did not allow rotation due to its triple bond structure. These observations show that single bonds allow rotation while double and triple bond restrict it. The bond length were also found to decrease in the order single bond is greater than double bond is greater than triple bond due to increasing bond strength. The concept of geometric isomerism was explored using different molecular models. Ethene and chloroethene showed no isomerism as the models were superimposable. Similarly, 1,1-dichloroethene produced only one structure. However, 1,2-dichloroethene formed two non-superimposable structures known as cis and trans isomer. This demonstrated that geometric isomerism occurs when there is a restricted rotation in the double bond on each carbon atom is bonded to two different groups. Overall, chloroethene was found to have three isomers. Optical isomerism was demonstrated using bromochlorofluoromethane, where two models were mirror image but not superimposable, indicating the presence of enantiomers. This occurs because the central carbon atom is bonded to four different groups, making it parallel. In contrast, chlorofluoromethane did not show optical isomerism because it contains two identical hydrogen atoms, making it a chiral. This shows that